Welcome. My name is David Katz, and I'm a principal consultant at Spotfire. And here's my co-presenter.
Hi, my name is Tomasz Jurczyk, and I am data scientist at Spotfire. Welcome to our session. So most probably you are now thinking, what is wrong with this penguin, which looks completely different than the rest than the others on the picture. But I suppose finding penguin or suspicious penguin is not that useful. However, I'm sure that what is useful is to find abnormal or not typical behavior of your processes. And for sure, in your industry, you have a high interest in revealing rare items or events in your data that deviate significantly from majority of the data. In that case, this is the right session for you because we will discuss anomaly detection methods. In our talk, we will first discuss a bit the common principles used for unsupervised anomaly detection in order to set up a scene for our universal anomaly detection application, which is published and any of you could use it for your tasks. David will show you the application together with examples, and also will spend some time on cool new features. The last point is a wrap up. So let me start with anomaly detection principles. Concerning assumptions, we are focusing on a very typical situation where we have multivariate data, which means data with many columns, and this data has a large volume. Also, we expect that we do not have labeled incidents, which means we do not know upfront before the modeling if situation is anomalous. So let me discuss a bit these common principles before we jump into ready application. If we take first the raw input data of cross-sectional data, typically this is a one row of multivariate data. We can apply some univariate methods for each variable separately. In that case, we will get into the problem that we have too many variables and many outliers might slip because they are not visible in one dimension. Like the classical example in the picture here, where there are clearly outliers, but they are not visible in any one-dimensional look. Looking at typical multivariate anomaly detection methods, like doing k-means, will not work because of high dimension. So these are not good approaches. What is recommended to resolve this is to use some dimensionality reduction method to lower the dimension and use classical multivariate methods like k-means. In that case, outliers are these which are small clusters or the points which are far away from the center of the cluster. Alternative is some overall measure, like hoteling t-square, for example, which is one number. And this approach is often used in practice. So this is one candidate for anomaly detection score so far. And reduced dimension here is in fact only a different look at the data. But what if we go further and create an advanced model, which will cover the typical behavior of the data, or in other words, normal operating conditions. In that case, we can extend this schema, and we are doing first already described encoding, which consists of finding a function that will reduce the data into a lower dimension. On that reduced space, a decoder is used, which will reconstruct the data back into original space. With a lot of data at hand, the expectation is that the model will cover the typical points as close as possible. And the bottleneck layer in the middle is in fact forcing the model to extract only relevant information and reduce noise. So now look at these layers and potential anomaly detection scores. So doing anomaly detection on reconstructed data layers doesn't make much sense because, and also the drawbacks are the same as in the original data. And the question is if it even makes sense. If we average the difference between reconstructed and original data, we will get reconstruction errors. These are good, but still the same problem as with original data. The advantage is that you can do an average or sum of all reconstruction errors, and we will get one number, and this number can be easily used for anomaly detection. It's typically called SPEQ, or in the context of autoencoders, simply overall reconstruction error. Another advantage is that we can check vector of reconstruction errors and get idea which variable is contributing the most to this overall reconstruction error. To understand more this encoder decoder and hoteling t-square and SPQ measures, let us show simple PCA illustration. For simplicity, we have only two-dimensional data at the beginning, which is this left picture. We can apply principal components and reduce the space to one dimension, which is this middle picture. And after that, we will reconstruct this one-dimensional data or one-dimensional projections back into two dimensions. This is this right picture. This is some simplification or model reducing noise, right? And on the very right graph, we can show or we can see how the reconstruction errors are calculated. If we look at hoteling t-square in PCA context, it's a measure of distance from the center in the projection space. So large t-square means the projection is somehow extreme and far away from the typical points. And this seems like a good measure of an anomaly. Unfortunately, hoteling t-square loses its interpretation when the encoding is much more complex than linear PCA. In addition, a large hoteling t-square is not saying anything about whether or not the point is satisfying our overall model. For that, we have a SPQ measure. If it's large, the point is too different from the typical behavior learned by the model. And if we are able to create the model generalizing data well, we would more logically stress the usage of SPEQ measure. So that was a bit of motivation behind, but David will show you a comprehensive application for anomaly detection, which is ready to be applied to your use cases. So the interesting part. And the application includes modeling based on this encoder-decoder principle and deciding based on this overall reconstruction error. The methods used for modeling are much more sophisticated than this simple PCA example and serve as a good alternative for PCA. So, David, over to you.
Thank you, Tomas. Let me give you a little preview of what I'm going to talk about, building on Tomas's excellent presentation. I'm going to continue to make a comparison between PCA and autoencoders. And then I'm going to look at a workflow of building a single autoencoder, which has been available as release 4. And then I'll go into release 5, which has a number of enhancements, which I want to concentrate on. The ability to build multiple models in a single run, a class system to support that, and using other packages to expand on it. And then we'll have a look at some of the model comparison visualizations and some actual examples of different data sets run through here. So contrasting and comparing autoencoders with PCA, the basic structure is the same. We build a simplified lower dimensional model and then look at where that model fails to fit. So the reconstruction error or the residuals are really what we're after. We're after a model of the normal operating conditions, but those are intermixed with anomalies or incidents, and the those differences, as Tomas was saying, help us understand what the anomalies are and what their root causes are. Autoencoders have a particular advantage in that they can work with noisy and non-normal data, which sometimes PCA struggles with. So as a motivating example, here's a very simple dimensionality reduction down to 2 dimensions. On the left, it's done with PCA. On the right, it's done with an autoencoder. And what we're looking at is the digit identification problem. MNIST is a frequently used benchmark. Here, we're just noticing that the autoencoder version does a better job separating the digits visually in just 2 dimensions. Of course, there are many more dimensions when you start with the image version of these digits. So here's a schematic of an autoencoder. Layer L1 is the input, L3 is the output, and the bottleneck layer that Tomas mentioned is here represented by a smaller number of nodes or neurons. And so we do get the lower dimensional version of the data out of this model, and then we can compare layer L3 to L1 and see what the reconstruction error is. So let's walk through the type of data that we start with. We start with a multidimensional time series, and a typical, time series analysis generally starts with looking at individual time series, but we take a different approach where we get a snapshot in time, which is represented by a vector of many values for the different variables. When we do it that way, the time dimension is mainly handled in the post-processing step visually, as you'll see. The first step, of course, is to create training validation test samples. What's unique to time series is that we generally use time-based splitting to prevent data leakage, peeking at the future, which you can't always do in real life. Then we select which variables are of interest in our particular analysis. We set the parameters on the left side here, and we get a result out of our training process. We get a learning curve, which shows the decreasing error over more and more training. And then on the right, we see the same data represented as a histogram. It shows the number of small reconstruction error on the left and the number of large reconstruction errors on the right. Those on the right represent the suspicious points that we are looking for, the anomalies. So then we go to the next view of the same data, but this time we're looking at it in a time series sense. So the x-axis is the time series, the y-axis is the reconstruction error. That gives us an insight that's not readily available without the time dimension, is that the high reconstruction errors, the anomalies, are clustered in time. So you get this typical kind of spike appearance. So if you focus in on one of these spikes, you can ask, well, what of our many dimensions are contributing to this high reconstruction error? Well, that's what you get from this bar chart. Programmatically, the data function is set up so whichever points you mark, it summarizes them and looks at them from the point of view of the contribution to the reconstruction error. And in fact, if you go ahead and mark the bar, you go ahead and you find the time series, which is on the bottom. It's the time series of the raw data of the variable you've selected, and the center panel is the contribution to the reconstruction error over time, and then the summary on the top, which is the total reconstruction error as of time. And then, of course, if you click on another one of the bar chart bars, you can see what's happening with this other variable DP2, which is contributing lesser but still significant amount of error to our low dimensional estimate. One thing that's very nice in this DXP, in this workflow, is, sometimes you have a bimodal distribution that actually represents 2 different regimes or states of the system. Here we have a high-powered regime, low power or idle situation with with process that we're monitoring. And it can be useful sometimes to concentrate our analysis just on one of these regimes, the one that's of more interest. And Spotfire lets you do that, and then goes ahead and does the rest of the analysis just on the points that you've marked. So that can be very useful. And moving forward, we see that not only do we want to be able to investigate these large incidents manually by marking them, as I've shown, we also want to programmatically find all of the incidents and do analysis on that level. So this lets the slider lets you adjust the cutoff point that you want to use, and then it looks for contiguous time stamps that indicate one of these incidents. So once you've done that, you have the ability to go ahead and cluster the incidents and even go ahead and show the time series of the clustered incidents. So for example, here we've got a case where we found two clusters and we get the profile of the two clusters, and we see how they're different. And this can help us if we're thinking about root cause analysis. What are the causes of cluster 2 and cluster 1? And here we plot them as time series, so you can see the clusters are color coded, and longer incidents are emphasized with a larger plot point. So our latest enhancements are interesting in that we can, as I mentioned, create multiple models. In other words, we can vary the kind of pre-processing we do for missing variables, missing data, and so forth. The model fit parameters, we can try different sets of model fit parameters, and then we can compare the results visually. And how do we do that? Well, what we've done is we've created in our Python data function, we've got a class system. And I call your attention to the subclasses for the two different types of models we currently support. Hopefully, we'll be enhancing these as we go forward. But the autoencoder model is the one we've been talking about primarily. But LSTM stands for long short-term memory. It's very effective in text applications, and here we're using it in a slightly different context. LSTM basically lets you use lagged variables. Lagged variables are very important. Also, on this slide, we wanted to do a call out to our other session, Mastering Time Series Analytics with Spotfire, where we have a package of Python functions, which, because of our class structure, you can integrate easily into this structure that this DXP provides. So look at how does this look in practice? We have a lot of parameters to manage. Each row on the bottom there is a set of parameters for one of our models. It also refers back in the last column to some strategies for data preparation. And you can manipulate these, edit these with this interface that's provided. So you can select a row and modify the parameters of that model that you might want to be adjusting. So now you have a collection of models that we run in a single run. And as we saw before, part of the result of these diagnostics, which include a model learning and also the error histograms. So we saw it in the context of a single model. Here we have multiple models, and comparing these results gives you insight into how well these models are doing if you want to select one or make further modifications. As an example, we have these two models, which are basically the same, except the second one is trained for a longer period of time. And so we've reduced the overall reconstruction error. Well, that sounds good, but of course it takes longer, it takes more computer time. Well, what have we actually gained? Well, when we look at the two histograms that we get from these, we see that the model that we spent more time on is not giving us very different results. And in fact, in a time series view, we see that these look almost identical. So the advantage here is that we've learned that in this context with this data, we probably don't need to train it to quite as long an extent. We can kind of take a shortcut, if you will, and be more productive in looking at different models. LSTM is a methodology of using lagged variables, but in the case of fitting neural networks with gradient descent, you need to make a more specialized algorithm, and that's what LSTM does. It makes it accessible in this context. And what that looks like in terms of our raw data means that you're not only looking at a single point in time, but you have a window, or the width here is generally called the look back parameter. Here we have these two models that we built. The LSTM model is on the right, and in this particular case, it's a little disappointing, is that we don't get as accurate a model here, and also the difference between the training and the validation is indicating that there might not be as much ability to generalize in this case. And also we look at these two side by side, or one on top of the other, and the plain autoencoder on the top does a better job of separating the normal operating conditions where the reconstruction error is small, and the incidence where it pops up and it's higher. So the bottom looks quite a bit more chaotic in terms of that distinction, and may prove to be less useful. So this is something that other people have seen, as the LSTM is not always the best, but then again, sometimes it is. So here's another example. Going back to the earlier one, this is where we're using both of the regimes, the high power regime and the low power regime. And here LSTM shows its ability to actually understand that difference, because it's looking back at the history, or the look back. And so we get a better fit with model 2 with the LSTM, and we also get a much nicer view of the normal operating conditions, where the errors are low, and then the spikes where the errors are high. So let's have a recap. That I'll turn it back to Tomas, so that he can wrap things up.
Thank you, David. Thanks for great examples and explanations. So let me summarize what we have learned. So the most important thing is that autoencoders really can be used to model normal operating conditions, even in presence of outliers. And also that reconstruction errors can identify anomalies in close analogy to PCA methods. Time dimension can be handled well by post-processing, and in visual analytics, or visual inspection has an important role, as we have seen, for understanding and interpretation of our results, right? And in many cases, also the comparison of multiple methods provides insights, which is also the reason why we incorporated this nice feature into the application. So as a next step, we would like to encourage you to try yourself on your data our anomaly detection template, which you have seen. It's a comprehensive, ready application with multiple model comparison. And we can recommend also our other resources, like our anomaly detection community page with many examples and use cases. Concerning time series topic, it was already mentioned that we would like to point your attention to another breakout session called Mastering Time Series Analytics with Spotfire. And also we would like to point you to our time series community page. So thanks for watching, and have a great day.